Alright guys, today we are going to do the LeetCode problem of the day for December 13th. It is 931 minimum falling path sum. The question asks, given an n by n array of integers matrix, return the minimum sum of any falling path through matrix. A falling path starts at any element in the first row and chooses the element in the next row that is either directly below it or diagonally left or diagonally right. Specifically, the next element from position row column will be, the diagonal, the one below it, or the diagonal to the right, and it's +1. So this is row 0, row 1, row 2. Okay, so as an example, it wants the minimum sum. So it says here 2, 1, 3. We can pick two minimum falling paths, so go 1, 5, 7 or 1, 4, 8. Okay. Here we have -19, -40, so that's the most obvious quote-unquote min sum. Okay, so the problem is pretty straightforward. Now, I'm actually going to do this problem both in C++ and in Python, but the pseudocode should relatively remain the same. So to reiterate, our goal is to find min sum path, falling path. Inputs are only parameter, matrix to traverse. Output, return the min sum. Okay, so how we're going to do this? Immediately, I noticed that we might have to go through. We have a decision tree, right? So we start off, we can pick any number in the top row, okay? So then we can go 2, and we pick 2, we can go 6 to 5, and so on. We can pick 1, we can go 1, 6, 1, 5, or 1, 4, and so on. And we start at 3, we can go 3, 5, and 3, 4, and so on, and repeat that for pretty much every row. I noticed that we can do a little bit of, we can break this down into its rawest form, like a dynamic programming problem, right? Because we're taking iterative steps from one row to the next. That's what I'm thinking. So what I'm thinking is say, okay, if I'm at this 7, what is the minimum sum going from 7 to the bottom? Well, that'd be 7 by itself. Same thing if I started at 8, 8 to the bottom, that'd be 8, 9 would be 9. Okay, save that in a DP table. Now, if I start at 6, I can either go 6 to 7 or 6 to 8. Now, the minimum path sum to go to the bottom would most obviously be 6 to 7, so that'd be 13. And I'd save that as a DP value here. And then that would be so on for the bottom. So starting from the bottom and going up like that, say 5, I can go 7, I can go 8 or 9. So here it would be 12. For 4, it would be 4, 8 or 4, 9. 4, 8 would be the best solution, so it's 12 here. So now I have another row in my DP table that's 13, 12, and 12. And then up here, I can go 2 to 13, or I can go 2 to 12. 2 to 12 is best, so that's 14. I can go 1 to 13 or 1 to 12. 1 to 12 is best, that's 13. And then 3 to 12 or 3 to 12 is the same, it's going to be 15. Now the fastest one is going to be 1 to 12, so that would be 13. 13 is our answer. So notice that we really only need 2 rows at a time, going up each step of the table, kind of like a DP problem. So pseudocode, 2 rows, 1 row, DP, save the value for the next row. Okay, and then we can go off of there. Okay. So the time complexity, before I skip any steps, let's just rewrite what I just said. So starting from bottom row, work way up, finding the min steps for each place in the array. Then find min sum of the array at last step. The time complexity for this is going to be O of n times m, because for each block we find its TP solution by assessing the 2 or 3 blocks below it, and we do that for every single block in the matrix. So that's n times m. Now the space complexity of this, since we talked about, we actually only need to save 2 rows at a time. That's going to be O of n times, or 2 times n, which simplifies to O of n space complexity. So only saving 2 rows at a time, and that is it. So let us discuss what, let's take a look at what that looks like. So we're going to have a vector of ints, and we're going to call this our DP, vector of ints, and we'll call this the quote-unquote above table, right? So, and then we'll have our int I is equal to matrix at 0 dot size. Now, before I do anything else, let's look at the constraints again. Make sure I'm not overstepping or not accounting for any test cases. It says that n must be at least 1 size. So we can safely assume this. We can access the first element, and then n is equal to matrix.length, matrix I.length, and then negative 100. It's within these values, and so on. Okay, so then we'll say while I is greater than or equal to 0. So we're working our way up, I minus minus. Okay, now we can say, we'll say this is minus 2. So we'll start on the second row. So we start on the second row. We're assuming there is going to be a second row. So first, let's account for the 1 row, case. So if matrix.size, the number of rows, is equal to, actually this should be dot size here because it's rows. If matrix.size is equal to 1, simply just return the minimum or min element of matrix at 0.begin to matrix at 0.end, and this should be a dereference. Okay. If it's only 1 row big, otherwise we will populate our DP row, DP dot, so for auto number in matrix, the last matrix, the last row of the matrix, we say DP dot push back our number. Okay. Now we are going to say cur row. So vector int cur row, let's say above is equal to matrix at I. So we're going to say, okay, let's say our above matrix is now going to be matrix at I. So that'd be 6, 5, 4. So for auto or in J equals 0, J is less than above dot size, J plus plus. We're going to say grab the below element. So we want the DP at, we want the DP element at J. So we want to grab the below elements, right? So how do we write that nice and cleanly is my question. So DP at J minus 1, we want above at J to equal DP, the min of DP of J minus 1, DP of J, and DP of J plus 1, right? Because if we're at 6, we want it to be the minimum of these values. J plus this should be plus equal. Okay. Now, of course, this is only if j minus 1 is within bounds. So let's do this. Int min dp is equal to dp at j. If j minus 1 is greater than 0, then min dp is equal to min of dp j minus 1. And then the same thing if j plus 1 is less than dp dot size j plus plus. Then we will say j plus 1, and then we can simply say min dp. So that's that value, and once we've calculated the correct dp values for this row now, we can say dp is equal to above and I minus minus. Now, of course, we can return the min element of dp in dp.n after we are finished. So to reiterate what we've done is if we only have one row, then we simply just return the min element of that one row. Sounds about right. Otherwise, we'll use a kind of dp tabulated solution here. We'll push back the last row and we'll start our iteration. We'll start here. We'll say, okay, let's let this quote unquote above row equal to matrix at I. So it's going to make a copy of it. It's going to say 654. Okay. Now 6 is going to be added to the minimum of dp at j, dp at j minus 1, dp at j minus 2, or j plus 1. So that would be 13 here. Above j would be 13. Go to the 5, that'll be 12. 4, it would be 8. And then, of course, now we don't need 7, 8, 9 anymore. We can just use 13, 12, and 12. And that will be our new dp for now this row here. Hope that makes sense. And that should be good to go. Of course, we min element the dp values once we have them at the top, and we return that. So we run this. Forgot. Check for any semicolons. So we run this, and it's accepted. Okay, cool. So that's the solution C++. How am I doing in time? I did 12 minutes. I guess we can add a couple more test cases. Let's add the 1x1 test case. Now, it's a square, so actually I can simply just do this. Return matrix x 0, 0, since it's going to be a 1x1. This is a square. I wrongly assumed that it's a rectangle. So fixing that time complexity. So now we have this, we can just return the element itself, and that should be it. It handles negatives, it handles big numbers, and we can go ahead and submit this. Wrong answer. Output negative 25, expected negative 36. So for this, I want to see out the DP. So for auto A and DP, we're going to see out A with a space, and of course see out a line break. So we're going to go ahead and add this as a test case. Let's run it and see what mistake we made. Okay, so we start with 51, 81, 69, negative 51, and then we go to negative 58. So negative 58 goes to 51, that makes sense. And then negative 51 goes to, it didn't go to 51, it went to 81 for some reason. So negative 51 should have gone to 51. For some reason it didn't, because this should be greater than or equal to 0. So run this again. Now it's accepted. So a little mistake here. It should be greater than or equal to 0, because we should be able to access the 0th element. So give it another submit, and that should look a lot better. Okay. Looks like we beat 5% of the answers, 69% of the memory. Now I'm curious how this could be done a little faster. So DP, 4 lines. Let's look at the CPP solutions. So I use for loops instead. Strange how my submission took quite a while to compute. It took 100 seconds. How much is this one? 16 milliseconds. And M. Oh. They reuse the matrix here. Here they use a solve function that involves DFS, but it has a DP. Interesting. So where's my, oh, of course. It's because I ran the, I have this C out. That should be better. Okay, there we go. Now it'd be 94%. Okay, there we go. Because I was C-outing some things. Okay. All right. Looks good to me. I think we could do a little optimization here. Matrix at matrix at size -1. And that would be a little bit faster, because instead of copying it and using the pushback function, it's used a constructor, and it's actually slower. Okay, well, that shouldn't matter too much. Now, as promised, I'm hitting the 20-minute mark. Let's go ahead and do this in Python 3. Now this should be a little more straightforward. And okay, so we have our DP row, the matrix minus the last matrix, and then our so while we have equals length matrix minus 2. See if length matrix is equal to 1, return matrix 0, 0. Just like we talked about before. While the matrix, we'll take the last row as the DP, and we'll say while I is greater than or equal to 0, we'll say our here, current, or above row, see this one? This matrix at I, we'll say for I in enumerate above, if I minus, so min dp is equal to dp at I, let's call this j, min dp is equal to dp at j, if j minus 1 is greater than or equal to 0, min dp is equal to min of dp at j minus 1. If j plus 1 is greater than, is less than or equal, less than dp dot size, min dp is equal to min of min dp So same thing as before. Adding it if it's in within bounds, and then we'll say once we have our min dp above at j plus equal min dp, and then we'll say dp is equal to above. Of course, this should be a copy of above. Don't want to mess that up. And then we'll return the min of dp at the end. So we'll run it, and that should be it. This is not size. I picked up some habits from my C++ programming, and that should be able to run. Oh, and of course, I -1. So wait for that to time limit exceed, and that should be it now. Cool. So we'll submit this, and we should be able to get this right for Python. Yes, beats 92%. So this is a very clean, tabulated way to do a DP problem. So yeah, hope you learned something from this video today, and catch you next time.